Hello everyone, I am Naman Khetan and I am an applied scientist at Amazon. So this is part 2 of our reinforcement learning course, and today the subtitle really is the whole story where we are going from planning to learning. Let me start by reminding us all what reinforcement learning really actually is, because it's easy to lose the definition in the math. So, reinforcement learning is learning what to do, how to map situations to actions so as to maximize a numerical reward signal. Notice what's special in that sentence. The learner is not told which actions to take. Nobody hands it a label data set of in this situation do this. Instead, it has to discover by trying things out which action yields the most reward, and those action can affect not just the immediate reward but the next situation, and through that every reward after it. So RL is defined by two features you don't see together anywhere else in machine learning: trial and error search and delayed reward. So part one gave us the language and the equation. Everything there was a definition or an identity. Part two is where the equation turns into algorithms that actually solve problems, starting from the ideal case where we know everything about the world and ending up with an agent that learns to play Atari games from knowing nothing about raw screen pixels. So here is the roadmap for the next 1.5 hour. I want you to notice that it's an organizer journey where each step removes an assumption. We start with a dynamic programming where we assume we know the world perfectly and just compute the answer. Then exploration versus exploitation, the fundamental question of what to even try when you don't know the world. Then multi-armed bandits, the simplest possible RL problem which strips everything down to pure exploration. Then the heart of the course, temporal difference learning, which learn directly from experience with no model at all. Then on policy versus off policy, a subtle but crucial distinction about where your data comes from. And finally, deep Q networks, where we bolt a new neural network onto all of this and get superhuman Atari. So two threads to hold on to the entire time. One, almost every algorithm today is a version of the same idea: update my estimate toward reward plus discounted future reward value. Two, there is a constant tension between using that what you already know and discovering something better. So keep those two ideas in your pocket and everything will connect. So what is dynamic programming in the RL context? It's a family of methods that compute the optimal policy, but only when you have full knowledge of the environment, the complete MDP. Let me be concrete about what full knowledge means, because this is exactly the assumption we'll spend the rest of the talk tearing down. You need to set you need the set of all states as the agent can be in, the set of all actions a it can take, the transition probability P of S dash given a state and an action, that is the dynamics, the probability of landing in state S prime if you take an action A in state S, the reward function R, the payoff for each transition, and the discount factor gamma between 0 and 1, which says how much we value future rewards versus immediate ones. Gamma near 0 means myopic, grab reward now. And gamma near 1 means far-sighted, be patient. The core idea of dynamic programming is beautiful and simple. Break a hard problem into simpler, overlapping sub problems, solve those and reuse the solutions. Here's the analogy I like. Think of a GPS with a complete map and live traffic data. It does not drive around trying different routes to see what is fastest. That would be learning. Instead, it computes the shortest route directly from the map. That's dynamic programming, planning on a known model. There are two classic DP algorithms we'll do next: policy iteration and value iteration. The wonderful thing is that both are guaranteed to find the optimal policy. So, policy evaluation: how good is my strategy? Before we can improve a policy, we need to be able to score one. That's this slide. It's called policy evaluation and it's the prediction step. The question is, given a fixed policy pi, what is the value function v pi of s? That's the expected total discounted reward if you start in state s and follow pi forever after. Look at the equation and let me translate it into plain English rather than symbols. If it says the value of a state is the average over all the action my policy might take of the immediate reward I get plus gamma times the value of wherever I end up. Now let me name each piece. V of s is what we are solving for. Pi a given s is the probability our policy picks action A. P s prime given s comma a is the environment's dynamics. R is the immediate reward. Gamma discounts the future, and the v s prime notice this is the value of the next state, which is itself something we are trying to compute. That self reference is the whole trick, and it's why we iterate. The algorithm couldn't be simpler. Start with v equals to 0 everywhere, then apply this equation over and over in sweeps across all states. Each sweep pushes reward information one more step backward through the state space. You stop when the values stop changing. That's iterative policy evaluation. Now let me show you a demo for this. Here I have an interactive version of this on a digital 3 by 3 grid with a plus 10 goal and a minus 10 pit. Under a purely random policy, the start cell value starts around minus 20 because a random walker keeps blundering into the pit. So what will happen is we'll start from this start space, and then the policies are random. So if we take a one sweep, so the value for this state becomes minus 3.25. This is because like uh, if we take for every step we have a minus one. So if we take a say left turn, left turn, then if you go left side, then we there's a wall. So we'll just go into the wall and come back here. So it will give us a reward of minus one, right? And then the v of the value of state s dash s prime, the s prime will be again the same state and its value is 0, so this part will become 0. So for the left turn we'll have a minus 1. If we go up, we'll have again we'll go in a state where initial the reward will be minus 1 plus gamma time 0.9, and the initial s prime state for this particular cells was also initially 0, so it becomes also minus 1. Same for if you go down, we'll hit a wall and come back into the state, so we'll get a reward of minus 1 plus gamma times value the value of the value of the s prime state, which is this state itself, which is again 0 in the beginning, so it will minus 1. If we go into the pit, then we'll get a minus 10 reward. So we'll get a minus 10 reward plus, and if you go into pit, we'll start from this state again. So it is minus 10 plus gamma times the value of the s prime state, which is again this state. So it was 0. So this gives us the value of minus 3.25. So if I do another sweep again, for all the four action, how we evaluate our policy, we'll get we'll take an average over all the actions, we'll keep getting the negative. This is a negative number is the honest uh, score of a bad policy. So it will keep going because every time it start in a pit. Cool. So now let's now go to the next part. Now that we can score a policy, we can improve it. Policy iteration alternates two steps. So step one, evaluate. Compute VPI for the current policy, exactly what we just did on the last slide. And step two, improve. At every state, switch to the action that gives the highest immediate reward plus discounted future value. You can see the argmax value, argmax A. So we are now basically taking the best action, the action which is giving the highest current reward plus the discount future discounted reward, and making our policy for that state choose that action. So why does this work? Because of the policy improvement theorem, which says if you greedily improve at every state, the new policy is guaranteed to be at least as good as the old one and usually strictly better. And since there are only finitely many policies and each round strictly improves until it can't, this process must converge to the optimal policy pi star. So the loop looks like this. Start with some policy pi 0, evaluate it to get v pi 0 and improve it to get pi 1, and you'll evaluate that, improve again pi 2 pi 3 until you reach pi star. But there's one catch, and it motivates the next slide. Step 1 is expensive. As you saw in our previous demonstration, that we were actually, no, we are stuck. We were like, we have to go through multiple iterations, right? So yeah, it's expensive, and fully evaluating a policy can take many sweeps on over every state, and you do not have to do that before each single improvement step. So now let me show you the demo for policy iteration. So yeah, so here everything revolves around Bellman equation. So like we saw a previous demo, so we are first if we'll evaluate as step one, and then once this the value function settles down, then we'll improve the policy and so forth. So in this, I start with deliberately terrible policy where every cell says go right, which means the cell next to the pit, which is our starting state, will always get a -10, right, as a reward. And now you can watch the evaluation make that cell's value crash toward -100. So if you see, if you let's run a one sweep. So if you see applying this Bellman equation, so we'll get if as we got into the pit from the for our starting point, we'll get a -10, right? -10 plus the gamma is set to 0.9, and because we were setting the pit, our S prime is again this state which was initially set to 0, right? So this way we'll get a -10. If you go next, again we are into this pit, right? So like we get a reward of -10 plus zero point 0.9, and as initial value was -10, so that's the value of our S prime state as per that policy. So we'll get a -19. And if we just keep going until until this value settles down, we'll see that it goes towards -100. You see, you see the delta is getting smaller and smaller. It will eventually. Now you see it's getting, it won't change. So basically it has settled down. Now let's improve the policy. So you see the one improvement flips it arrow to point up and around the pit, and the whole thing converges in around 5 rounds. So yeah, now let's talk about a clever approach: value iteration. So why bother fully evaluating a policy before improving it? What if we fold the two step into one, and that's the value iteration for you? The change is tiny but powerful. And look at the equation. The only difference from policy evaluation is that we replace the policy weighted average, the sum over actions of pi times everything, with the max single max. Instead of averaging over what our current policy does, we directly take the value of the best action. That one substitution merges evaluation and improvement into a single update. The algorithm initiate V to 0 for every state, set Vs to the best action expected value, repeat until the values stop changing, then read off the final policy by taking the RMX, the best action in each state. Quick comparison of the two DP methods. Policy iteration, fewer outer loops, but each loop includes a full expensive evaluation. And then value iteration, more outer loops, but each loop is a single cheap sweep. In practice, for large problems, value iteration is often preferred. But here's a punchline that sets up the entire rest of the talk. Both of these methods require the full model, the transition probability, the probability of S prime given S state and an action. And in real world, we almost never have that. So as elegant as DP is, we need something that can learn without a model. Now let's go to see the demo. So yeah, here's a demo for value iteration. So in this demo, you can literally watch the value spread outwards from plus 10 goal, one ring per sweep until the send converges to about 4.58. So you see the first in the even the best move from the start is the one going upwards, and if I run the auto sweep, it will just converge in just 4.58 in just 5 sweep. So yeah, this is pretty great. Now let's talk about the limitation. Like we know, like for small, fully known problems, dynamic programming is perfect. Now the honest part. These three limitations are precisely what the best of the course exists to fix. One, DP needs the complete model. A real robot doesn't have transition equation for every surface it might roll over. Two, the curse of dimensionality. DP sweeps over every state on every iteration. Chess is around 10 to the power 47 states. Go has 10 to the power 170. And Atari screen is in fact effectively infinite. You cannot sweep those, right? And third, it only works for discrete finite state and action spaces. So continuous control like the joint angles of a robot arm is simply out of scope. So the takeaway is this. We need methods that learn from experience without a model. And the moment we start learning by trying things, a brand new problem appears. What should we even try? That question is the next section. The instant we stop being handed the model and have to learn it, we hit the most fundamental tension in all of decision making: exploration versus exploitation. It shows up everywhere, from A/B tests to clinical trials to how you choose a restaurant tonight. Let's unpack it. Every language agent faces these trade-offs. Let me define both sides sharply. Exploit means pick the action with the highest estimated value, use what you already know. The upside is you maximize your expected reward right now. The downside is you might be permanently stuck with the choice that only looks best. You never tried the alternatives. That's always going to your favorite restaurant and never discovering a better one. Explore means deliberately pick a more uncertain action to gather information, try something new. The upside is you might discover something much better. The downside is it costs you reward now because the new thing might be worse. That's trying the restaurant that just opened. Why is this genuinely hard? Because pure exploitation gets you stuck in a local optimum. You never find the global best. And pure exploration means you never actually cash in on what you have learned. The practical answer is to explore more early when you know nothing and information is precious, and exploit more later once you understand the landscape. The Amazon framing makes it real. Do we show the customer the product we know they click on? That's exploit. Or do we test a new listing that might convert every ever even better? That's explore. Every recommendation engine and ad system on earth lives on this trade-off. The epsilon greedy strategy. It's the simplest strategy that actually works. The rule: with probability 1 minus epsilon, take the greedy action, the one with the highest Q value. With probability epsilon, take a completely random action. So if epsilon is zero point 0.1, you exploit 90% of the time and exploit 90% of the time and explore 10% of time. That's a better version, a decay epsilon over time. Start epsilon near 1, almost pure exploration when you know nothing, and slowly anneal it down towards zero point zero 0.01. Explore heavily early, exploit heavily late. This also gives you convergence guarantees in the limits. The pros: it's trivially simple, it makes no assumption about the rewards, and it's shockingly strong baseline. The con is right there in the word random. Exploration is uniform, so a clearly terrible action gets the exact same exploration probability as a genuinely promising one. You waste part of your exploration budget on things you already know are bad. And this isn't a toy. TQN, which we'll see at the end, uses epsilon greedy with epsilon decaying from 1 to down to zero point 0.1 over a million frames. There are two smarter strategies that fix epsilon greedy's uniform random weakness. Softmax, also called Boltzmann exploration, instead of best or random, we turn Q values into probabilities. The probability of an action is proportional to e to the power q of over tau. That tau is a temperature knob. Where tau goes to infinity, all action becomes equally likely. Pure exploration. When tau goes to zero, you always pick the best. Pure exploitation. The advantage over epsilon greedy is that softmax explore in proportion to value, so it doesn't waste trials on obviously terrible action. A slightly worse action gets slightly less probability and not equal probability. Then let's talk about UCB, upper confidence bound. Here you pick the actions that maximize its estimate plus an uncertainty bonus, Q of A plus C times the square root of natural log T over N of A. The second term is the clever part. N of A is how many actions you have tried action A. So a rarely tried action has a small n and therefore a big bonus, which pushes you to try it. A frequently tried action has a small bonus, so you can exploit it. The slogan is be optimistic in the face of uncertainty. UCB needs no epsilon schedule, no temperature, and it's self-adapting, and it has provably optimal regret bounds on the order of square root of k t log t. So quick ranking, epsilon greedy is the simple baseline. Softmax is smarter but needs tuning. UCB is the most principled and tune itself. Now let's go to the next section, multi-arm bandits. N- Let's strip reinforcement learning down to its simplest form. A setting where exploration is the only problem, where with no states, no planning at all. These are multi-arm bandits, and despite being the simplest RL settings, they are the most widely deployed in industry. Picture a row of K slot machine. one-armed bandits, hence the name, which each with its own unknown payout rate. At each step, you'll pull one arm and receive a random reward from the arms distribution. Your goal is to maximize total reward over T pulls, and the catch is the whole game. You don't know which arm is best, so you have to discover it. And every pull you spend discovering is a pull you didn't spend on the best arm. Why is this the simplest RL problem? Because there are no states. It's the same situation every time. There are no transitions. Pulling an arm doesn't change the world. There is no planning. It's a pure exploration versus exploitation. Nothing else. The scoreboard for bandit algorithms is regret. Regret equals the best arms mean times T minus your actual total rewards. In words, how much reward did you lose compared to an oracle who always pulled the best arm? Lower regret is better, and the best algorithm achieve regret that grows only like the square root of t, which means the average regret per pull shrinks to zero. And this is not academic. Bandits are everywhere in industry. A/B testing, ad selection, clinical trials, product recommendation, search ranking, dynamic pricing. Everywhere, anywhere you repeatedly choose under uncertainty and get quick feedback, you have a bandit. Now, one powerful upgrade. A plain bandit gives the same answer to everyone. Which arm is best? A contextual bandit asks a sharper question. Which arm is best for this context? The loop. First, you observe a context X, your user features, time of day, location. Then you choose an action from your K arms, which ad, which product, which page layout to show. Then you receive an immediate reward, a click, a purchase, some engagement, and you learn which actions works best for which context. Here is the key distinction from full RL, and its industry love this setting. The reward is immediate. Your action does not change the future state. There are no delayed consequences to reason, but no long horizon credit assignment. So think of spectrum. Plain multi-arm bandit have no context. Contextual bandit add context but keep rewards immediate. A full RL adds the hard part, action that affect future states and future rewards. Contextual bandits sit in the sweet spot of usual and tractable. The Amazon example. A user is browsing electronics and it's evening, they are in Seattle. That context goes into the model which picks which of the five recommendation widgets to show. The user clicks and the model updates its belief about what works for that kind of context. That's personalization at scale. This next section is the heart of the course. So far, we have either needed a full model or we have been in the stateless bandit world. Now we finally do the real thing. Learn a value function directly from experience with no model, updating on every single step. This is temporal difference learning, and TD contains the single most important update rule in all of RL. Let me place TD between two things you already know. Look at the table. Dynamic programming needs a model, but it updates every step and it bootstraps. Monte Carlo learning is model free, great, but it also has to wait until the episode ends to learn anything and it doesn't bootstrap. TD learning is model free like Monte Carlo and it updates every step like DP and it bootstrap. It genuinely takes the best of both. I have to define bootstrapping carefully because it's the crux of everything that follows. Bootstrapping means updating an estimate using another estimate rather than waiting for the true final outcome. DP bootstraps of a known model. TD bootstrap of its own current guesses about the future. It improves a guess using a slightly better guess. Now, why is TD so powerful in practice? At first, it's model free, no transition probability needed. Second, it's online. You learn mid episode, you don't wait for the end. It works in continuing, never ending tasks where Monte Carlo simply can't. and it has lower variance than Monte Carlo, though it pays for that with a little bias from the bootstrapping. Bottom line, TED is most widely used family of algorithm in all of reinforcement learning. If you remember one equation from today, make it this one. Vs get updated to Vs plus alpha times in brackets R plus gamma Vs prime minus Vs. Let me name every single symbol. Vs is a current estimate of the state's value. Alpha is the learning rate. A small step like 0 0.1, controlling how much we adjust. R is the reward we actually received. Gamma is the discount, and Vs prime is the current estimate of the next state's value. Now there are two pieces you must know by name. The quantity R plus gamma Vs prime is called the TD target. It's a fresh, usually better estimate of what state S is really worth. And the full bracket R plus gamma S prime minus Vs is the TD error, return delta. That delta is the surprise, the gap between what we expected and what we just experienced, and is the learning goal. Here's the whole thing in plain English. I thought state S was worth Vs. Then I took a step and got reward R and landed in state S prime, which I currently think is worth Vs prime. So actually S is worth about R plus gamma Vs prime. I was off by the TD error, so let me nudge my estimate of Vs a small fraction alpha towards a better target. And the key thing that makes TD special, we update immediately one immediately after one step using our own estimate of the future. We do not need the true return and we do not wait for the episode to end. Now let's look at the TD0 learning demonstration. The TD0 grid demo walks the agent around. After each step, only the cell it just left changes, nudges by alpha times delta. When it falls in the pit, you see a big negative delta. Tease that neighborhood to stay away. You see here. So we are just computing R plus gamma times Vs prime, and we already know the Vs in the last state. So if you do auto walk, you see it's how it's learning for every state. You can do these calculations on yourself. This way we update TD. Now look at SARSA, on policy TD control. So far TD learned VS, the value of states. The actually control to choose action we need Q of S comma A, the value of taking action A in state AS. SARSA is TD applied to Q value. The name literally spells out the first five things in the update: state, action, reward, next state, next action. The update Q of S comma A gets nudged towards R plus gamma times Q S prime A prime minus Q of S comma A. The crucial word on this side is actually the A prime is the action we will take next, chosen by a real policy, including its exploratory epsilon greedy moves. So if a policy sometimes explores and occasionally does something risky, SARSA values include that exploration cost. It learns the value of the policy it is actually following. That's what on policy means. The algorithm in 5 lines. In state S, pick action A with epsilon greedy, take it, get reward R, and land in S prime. In S prime, pick the next section A prime with the same epsilon greedy policy. Update Q S comma A with the equation, then shift S becomes S prime, A becomes A prime, and repeat. The consequence which sets up the famous example 2 slides from now. Sarsa learns a safe policy, one that accounts for its own exploration. So now this is the SARSA policy. Now we can talk about Q learning of policy TD control. This is the most important single algorithm in the course and it differs from SARSA by exactly one word. Instead of using Q S prime A prime, the action we actually took, Q learning uses max over A prime of QS prime A prime, the value of the best possible next action. So the update always aims at the value of the optimal move regardless of what the agent actually did. Think about what that unlocks. The agent can explore widely, even take completely random actions, and still learn the optimal policy. Because the learning target ignores the exploration, it can learn from data collected by other agents or by humans. It the thing it's learning about the optimal policy is different from the thing generating its behavior. The exploratory policy, the gap is exactly what off policy means. Why does Q learning dominate the field? It converges to the optimal Q star regardless of your exploration strategy. As long as you keep visiting every state action pair, it's actually simpler than SARSA because you don't need to choose A prime before updating. And most importantly for this talk, it enables experience replay using old data, which is the foundation of DQN. This is Watkins 1989, one of the most influential papers in the entire history of reinforcement learning. So let's talk about SARSA versus Q learning. Q learning learns the optimal policy, the shortest path, because its max target assume it all will always act greedily afterward. But here's the twist. During training, those random 10% step occasionally knock it off right off the cliff. Optimal final policy, risky ride getting there. Sarsa learns a longer, safer path that stays away from the edge. Why? Because its own target knows it sometimes explores. So it factor in the risk that a random step near the edge would be catastrophic. It deliberately learns its distance. The one liner to write on the board. Sarsa is safe learner. Q learning is the optimal learner. Now let's talk about a demonstration to show SARSA versus Q learning. So first you can read that the agent at the center cell. Let's take this one concrete update. Say agent at the center cell took a right, landed on the cell left of the goal. Reward -1. At the next cell of values are these q of going above is 3, going down is 8, left is 4 and right is 3.5. And because of epsilon exploration, the action usually taken next was going up, not the best. Currently q center comma right is 50. So let's see the update for both. So sarsa, the update gets it to 3.74, while the q learning get it to 5.64. And now if we train both these for say 800 episodes, so you will see Sarsa assign the cell above the pit a lower lower value than Q learning does, because Sarsa prices in the chance of slipping in. The same idea, smaller stage. We just saw two algorithms that differ by a single word, max. It turns out that one word encodes a deep distinction about where your training data comes from. And that distinction is what unlocks the data efficiency behind modern deep RL. And let's make it precise. The core distinction. There are two policy quietly at play in any RL algorithm. The behavior policy B is the one that generates the data, what the agent actually does. The target policy pi is the one you are trying to learn. On policy means B equals pi. I learn about the very strategy I am following. SARSA is on policy. The pro is stability. It accounts for exploration noise honestly. The cons, its data goes stale the moment the policy changes, so you can't reuse old experience, which makes it less sufficient sample efficient. Off policy means B is not pi. I learn the optimal strategy while doing something else. Q learning is off policy. The pros are huge. You can learn from old data, from other agents, even from human demonstration. And critically, it enables experience replay. The con, it can be unstable, and that's the deadly triad we are about to meet. The theme to carry forward of policy is harder but far more powerful because it unlocks data efficiency. Two ideas here, one a superpower, one a warning. The superpower is experienced replay, and it's only possible because Q learning is off policy. The idea, store every experience, the tuple, state, action, reward, next state in a big memory buffer. Then, to learn, randomly sample old experiences and train on them. Each experience gets reused 10 to 100 times, which is incredibly data efficient. On policy methods cannot do this because their data becomes stale the instant the policy shifts. Now the warning, the deadly triad, when you combine all three of one of policy learning, two function approximation, meaning a neural network instead of a lookup table, and three bootstrapping, updating estimates from other estimates. The learning can diverge with values exploding to infinity. And here is the subtle part. Any two of three are fine. It's only when three comes together that things blow up, which is a great cliffhanger because DQN, the very next section, deliberately uses all three at once and then adds two clever tricks to keep it stable. Experience replay to decorrelate the data and a target network to stabilize the bootstrap target. Let's go see it. Now let's talk about deep Q networks. This is the payoff. Everything up to now use tables of numbers. Now we replace that table with a neural network, and the result is an agent that learned to play Atari games from raw pixels. DeepMind to 2015, the result that launched the entire modern deep RL era. Why do we need neural networks in reinforcement learning? Tabular Q learning keeps one entry for every state action pair. That's fine for small words like tic tac toe has about 5,000 states or taxi grid word has 500. You can store that table. But it collapses on real problems. An Atari screen is 210 by 160 pixels times three color channels. That's more possible states than there are atoms in universe. You can't store that table. You would essentially never see the same exact frame twice. So a table gives you a zero generalization. It has no idea that two nearly identical screens should have similar values. The solution is function approximation. Replace the Q table with a neural network. The input is the state, the game pixel. The output is a Q value for each possible action, and the magic word is to generalize a network that learns that similar looking state should have similar Q values. So instead of memorizing every screen, it learns visual patterns. We write it as Q S comma A theta approximately equals to Q star S comma A, where theta is the network's weight and one forward pass gives you the Q value for all action at once, so you can just make the max. Three problems with native deep Q learning. Now set expectations. If you just swap the table for a neural network, nothing else, it does not work. Here's why. Three problems. Problem 1, correlated training data. Consecutive game frames are almost identical, but neural network need diverse, roughly independent samples. Train on a correlated stream and the network offers to whatever just happened and suffer catastrophic forgetting of earlier lessons. Problem 2, non-stationary moving targets. The Q learning target is R plus gamma times max Q of S prime comma A prime comma theta. And notice it depends on theta. It's very weight we are updating. So every time we adjust a network, the target we are chasing also moves. It's like trying to hit a target that jumps every time you step toward it. Result, oscillation and divergence. Problem 3,
The deadly triad we just met of policy plus function approximation plus bootstrapping equals instability. DQN has all three. DeepMind's to 2015 DQN introduced two tricks that solve problems 1 and 2. By doing so, they frame the triad. Let's take them one at a time. DQN trick 1 Experience replay. Trick 1 Experience replay store experiences and train on random samples of them. Mechanically, as the agent plays, it pushes each transition state, action, reward, next state into a replay buffer, holding around 1 million recent transitions in a circular buffer that overrides the oldest. To train its samples, a random mini batch of 32 transactions does one gradient step on them. Why does this fix problem 1? Because a random draw from a million experiences is diverse and decorrelated. A single batch might contain a frame from level 1, a frame from the moment of death, and a power up frame all mixed together. That variety is exactly what the network needs to learn robust features instead of overfitting to the last few seconds of the play. Bonus benefits: data efficiency. Since each experiment experience is used many times instead of once, and smoother learning because you're averaging over many past behaviors and remember the through line. This is only possible because Q learning is off policy. Sarsa couldn't replay old data because it needs the action its current policy would take next. Sequential trick 2 The target network. Compute the learning target with a frozen copy of the network. You keep two copies. The online network theta is updated every single step. That's the student. The target network theta minus is a frozen copy, updated only every C step. In the paper, every 10,000 step. The loss function uses the frozen network for the target. It's r plus gamma times max cube s prime a prime theta minus comma minus q s comma a theta all squared. The frozen teacher provides a stable target, the student learns toward it. Why does this fix problem 2, the moving target? Because now the target stays fixed for 10,000 steps, giving the student a stationary objective it can actually converge toward. My analogy, it's like studying from a textbook that only gets a new edition each semester instead of one that rewrites itself every night. Then every 10,000 steps you copy the student to a teacher, the theta minus get to the theta and repeat. Plus the tricks together, the two tricks together, replay fixes correlated data and the target network fixes the moving target. And together you get deep Q learning that actually reliably works. Let's assemble the whole thing. I'll take walk the loop slowly. Initialize a replay buffer D with capacity 1 million, the online queue network theta with random weights and a target network theta minus set equal to theta. Then loop forever. Step 1. Observe the screen, stacking the last 4 frames into a 84 by 84 by A4 input. Step 2. Choose an action. Epsilon greedy from Q of S using theta with epsilon decaying from 1 to down to 0.1. Step 3. Execute it in the game. Get reward R and the next screen S prime. Step 4. Store the transition S, A, R, S prime in the buffer. Step 5. Sample a random mini batch of 32 from the buffer. Step 6. Compute the targets. Y equals R plus gamma time max Q S prime A prime theta minus using the frozen network. Step 7. Train. Gradient descent to minimize. Y minus Q S A theta squared. And step 8. Every 10,000 copy theta into theta minus. And the punchline that still amazes me this exact same algorithm with the same exact hyperparameters were applied to 49 different Atari games. No game specific engine, just raw pixels and actions out. Now let's talk about DQN network architecture. Here's the actual network. Read it top to bottom. Input is 84 by 84 cross 4, then a convolution with 32 filter, 8 by 8 stride 4, stride 4 and a ReLU, then 64 filters 4 by 4 and stride 2 ReLU. Then 64 filter 3 by 3 stride 1 ReLU, then a fully connected layer of 512 neurons and followed by ReLU, and finally an output layer giving one Q value per action. Now the design rationally, because these are strict exactly the question people ask: why four stacked frames? A single frame is ambiguous. Is the ball going up or down? Four frames encode velocity and direction. Why grayscale shrunk to 84 by 84? Color really matters for gameplay, and smaller inputs train faster. You can ask why convolutions. Images have spatial structure, and CNN detects pattern, edges, shapes, objects, regardless of where they appear on the screen. Why output all Q values at once? One forward pass gives Q for every action, so you argument instantly, far faster than running the network once per action. And again, the same architecture for all 49 games. No per game feature, no per game tuning. Now let's talk about DQN results. DeepMind 2015 Nature paper. Let's look at the results. On the table, you see the range superhuman on breakout, about 13 times human. Superhuman on Pong, above human on Space Invaders, more than double human on Enduro. And it's honest about failures too. On Sequest, it was still below human because that game needs longer term planning than DQN struggled with. The headline numbers: DQN beats human level performance on 29 of 49 games using the same algorithm architecture hyperparameters from raw pixel only. No game rules, no handcrafted feature, and the fun part, the strategy it discovered on its own. In breakout, it learned to tunnel a channel up the side and bounce the ball behind the wall to rack up points. In Pong, it learned to angle shots to the unreturnable. Nobody programmed those. Why did this matter so much? It was the first general purpose agent to master many different tasks from raw perception. It moved deep learning plus RL could work at scale, and it led directly to AlphaGo in 2016, OpenAI 5 in 2019, and essentially all of deep RL. It was published in Nature and is one of the most cited AI papers of the decade. Now let's talk about DQN variants. DQN kicked off a wave of improvements, four to known, one line each. Double DQN, which was published in 2016, the max operator systematically overestimates Q values. To fix, use the online network to select the action, but the target network to evaluate it. Result: more accurate values. Dueling DQN, again in 2016. In many states, the action barely matters. So split the network into two streams. How good is this state plus how much does each action help? Result: faster learning where the action choice isn't critical. Prioritize experience replay. 2016. Uniform sampling wastes time on boring transitions. Instead, sample the transition with high TD error, the surprising informative ones more often. Result: faster, better use of the buffer. Rainbow 2017. Combine six of these improvements together and reach about 230% of human median performance on Atari. The lesson is that these advances are complementary, not competing. Now let's try the whole journey together and notice how each step removed an assumption. 1. Dynamic programming with a full model compute the optimal policy exactly. Bellman updates and the policy improvement theorem. 2. Exploration versus exploitation. Epsilon greedy, softmax, UCB, how to balance using knowledge against gaining it. 3. Multi-arm bandits, the simplest RL. Contextual bandits add features for personalization. 4. TD learning. Learn from every step. The TD error is actual minus expected. No model, no waiting for the episode to end. The foundation of model error. 5. One policy versus off policy. Sarsa is safe. Q learning is optimal, and off policy is what enables experience replay and data efficiency. 6. DQN. A neural Q function plus replay plus a target network equals stable deep RL. A superhuman Atari from pixels. And here's a hook from what's next. DQN has a hard limitation. It needs discrete action because it takes an argument over a finite set. But what about continuous actions? A steering wheel angle, a robot joint, torque, or where there are infinitely many choices. You can't argmax over infinity. That is exactly the problem part 3 solves. Thank you for attending this, and let me leave you with the 5 things to remember. 1. DP is planning with full model. TD is learning from experience. 2. The TD error delta is the surprise signal that drives all TD learning. 3. Q learning is off policy, which enables replay, which enables DQN. 4. DQN equals a net Q network plus experience replay plus a target network. 5. The result, one algorithm raw pixels in superhuman on 29 Atari games. And a glimpse of part 3, where we tackle everything about DKN can't do. We will start with policy gradient methods, which optimize the policy directly and naturally handle continuous actions. Then actor critic methods, then a look at multi-agent RL, then RL with human feedback, and it RLHF and its direct connection to how modern large language models are aligned. We'll be honest about the challenges, sample efficiency, reward shaping, rewards, sparse rewards, and stability. And we will survey the frameworks and tools you actually use. And we'll close with a hands-on demo, training a DQN or PPO agent yourself. That's part 2 from planning to learning. Thank you, and I'll love to see you in part 3.